Thanks for having me, Lake Committee members. Is this your first, Seth? Second. In 1996, I left the Great Lakes Science Center for a job at University of Wisconsin-Stevens Point. And because I was on a academic year salary, I was going to try to make a full year of living, and I had to launch a research program. Well, I had 11 years as chair of the Lake Superior Technical Committee to at least think about what I would want to do on Lake Superior. So I basically stole a little conceptual model from the classic book by Bill Ricker on computation of fishery statistics. And it's the one that everybody who teaches about dicourse, which I did for 17 years, it has a box for the stock of fish and 2 inputs and 2 outputs. The 2 inputs are for somatic growth of fish, and the other one is for recruitment. And then the outputs, at least for an exploited stock, are natural and fishing mortality. So I built a research program around that simple conceptual model, and today is the end of it. Seriously, this is the end of it. I'm no longer employed by UWSP, but that conceptual model was brought to fruition through the last 3 graduate students that we've just finished up recently, and this presentation will at least attempt to synthesize that information for you today. And it came about in the end by working closely. We talked about that all day in the comment session. I was the chair of the tech committee, and then after I stepped down, I still interacted extensively with my partners in Wisconsin and other agencies. And at one point, my friend Steve Schramm and I were talking. I just finished a Sea Grant project and said, well, what do we want to do next, Steve? And he brought up this thing, the Gull and Shoal. So there's Citizen Steve holding a lovely fish from Gull Island Shoal. And Steve knew in the offing that his agency, the Wisconsin DNR, was eventually engaged in some negotiations with the tribal partners on Lake Superior for a new fishing agreement. And without saying how that might go, he said, I want at least to have evaluated the refuge so that the negotiators at least have all that information when they consider the future fate of the refuge, if they do. Not that they wouldn't necessarily bring it up. And I immediately thought back to a graph that Steve Schramm showed at a meeting of this group a few years ago, the most horrific graph I've ever seen in a meeting. The 2 panels are left and right. On the left, it's outside the refuge, and on the right, it's inside the refuge, and these are the age structures from standardized gill nets set at the same time in and out of the refuge. The sad part here is that the age structure outside the refuge means the fish, if you're female, are not even getting old enough to spawn. So this means one thing to me. I call it stock collapse. And at the time that Steve showed this, we all looked around at one another and said, we better get our resumes ready because we're here for the second collapse. So part of the story here goes back much further, and the basic idea behind all of our work on Lake Superior is that we were trying to restore stocks because they had basically all plunged to near extinction from overfishing and sea life predation. And then, of course, through a lot of things that happened in this room over many, many years, regulating fisheries and controlling sea lampreys and stocking, they recovered. One piece of that management puzzle was this little piece of real estate in Lake Superior that sits on top of a spawning area in the Apostle Islands. That refuge was created in 1976, and up to this point, never been, I would say, completely evaluated. And so Steve's motivation here was, let's do this, let's get it on the table so that if anyone wants to consider the future fate of the refuge, they'll at least have all the information they need. And I think that was very futuristic. Where's anyway. So the future of the refuge depends on a proper understanding of its role, both historically, putting us where we are today, but also looking forward into the future, which we can do with models to say what would be the likely effect of just lifting it, going in and fishing. And it's reasonable to think if stocks are restored, yeah, you can go in and fish. So I'll attempt to show you why that might be good or bad. So the refuge is not a huge chunk of Lake Superior. Notice on this map, this is inside this box, which is a small piece of the total real estate, but it's a complex of islands. And this refuge was constructed for reasons that are probably only now known to those that did it. But there's a little shoal called Gull Shoal right in the middle of it. Well, not in the middle of it, but that shoal was historically important. Fish spawned there ever since they probably first started after the glaciers receded. So the point is, what role does that little chunk of real estate play in this part of Lake Superior? And then at the end, I'll bring a third project in that shows you what role this area plays in the whole lake. And hopefully, when I'm done, this won't be totally confused. This is a relatively long-term picture of wild and stocked lake trout abundance in Lake Superior, and it's a terrific message on one level because now we have all wild fish and we don't need to stock. But there is no clear picture of what the role of the refuge is. Fishing was closed in 1962 when the first round of sea lamprey control had been instituted, and it was clear that we could get a hold of that problem. The managers immediately put a moratorium on fishing to save whatever few fish might be left. And Wisconsin eventually established this refuge in 1976. And notice that you could probably conclude what you want here, but whoops. Wild fish have been going up and the stock fish have gone away. And a lot of the reason that this is down now in the end of this time series is because we stopped stocking, right? You don't need to continue stocking when the fish are reproducing themselves. So the objective for the project is simple, just evaluate both the historical effectiveness and then the future need for this refuge. And I'm going to show you three parts of that. These were teased apart into three graduate student projects, and these are the culminating studies that were built around that conceptual model. Some of the people in this room participated unknowingly in this grand scheme of mine. Lisa's sitting up there. I thought I saw Jessica earlier. They built pieces of the puzzle that we're going to show you. So the historical effectiveness was a retrospective analysis, relatively simple, compare metrics of lake trout in and out of the refuge. The second part was a prospective modeling study. You simulate into the future based on a reasonably parameterized model. And then you turn fishing on and off in the refuge. Then the third part was what is the role of this zone in movement among all these areas, and how does that place WI2, this one little zone, in the context of movement rates among all the zones? And that's really a source sink dynamics question. So the retrospective analysis first. And again, we asked a simple question here. Let's take some statistics from all the netting in and out of the refuge and just compare them and see if they come out as we would expect. So you start out by saying my hypothesis is this thing should be higher or lower in the refuge based on what I think is going on. First thing I'll tell you is that a lot of fishing has been done in this area by a lot of people over a lot of years. Three primary data streams. The spring survey actually was built on the collapse of stocks and prosecuted with a standardized gill net that's not been changed since 1959. That beginning of that time series I showed you. That is a deliberate attempt to index the adult fraction of the population. The summer graded mesh survey was instituted later, and it was a broader scale, a range of nets to basically get at more of the whole population. And then the autumn survey is done at one location where they spawn, and it's a source of getting enormous numbers of fish tagged. So that became the source of information for us, linking the refuge to the non-refuge waters. How often did the fish leave? What's the likelihood that a fish caught in the shoal in the fall of this year will be outside the refuge next year? So this is just a little map that shows you the distribution of the netting. It's fairly comprehensive, and for phase one here, we're comparing the captures in these survey gears inside and outside. So for abundance, we just wanted to compare relative abundance in the sense of a catch per net night, and we have all these standard methods deployed in Superior to compare them inside and out. And the hypothesis here, of course, would be that abundance would be higher inside than outside the refuge, one would hope. So very simply then, this shows you the stockfish abundance, and the key feature here is that stockfish are going away. It's not that we're interested in them at this point. They've done their job. right? They helped in what way they could to bring about this picture. So these are the wild fish abundances from those surveys, inside and outside. And I think it's pretty clear. I don't have to show you a T statistic for you to know that there's more fish inside the refuge. So what I did, the samples of biological data are often too small in a single year because they're not trying to kill fish here. They basically take fish that die and then look at their otoliths. So we broke the whole time series up into approximate cycle time periods, and I'll show you graphs that take the biological statistics in those 4 stanzas. So first, growth. Basically, you fit a growth curve to the biological data for each of those periods. And compare them and say that my thinking would be that the growth will be slower inside the refuge because the density should be higher and they should be growing slower. Yeah, well. So this shows inside and outside. And the first thing to notice is that the fish are not old. They're only getting about this old, very early in the period, and you can't even fit a growth curve to the outside the refuge, which are these open dots, and then actually a curve does fit for strange reasons of nonlinear estimation. But let's step forward in the next 3 stanzas now, moving forward in time and seeing how the growth curves change. The first thing you notice is when you do have enough ages to fit the model, the growth is the same inside and outside. And you of course expect lag effects, right? It takes a while for the population to signal you that density dependence is happening. But notice as we move forward in time now, the refuge fish are growing to a shorter asymptotic length. Normally, I would think, if they grow slower, they're going to get to some larger size. And that persisted in the 2 periods. So I'm going to reduce it down now to omega, which is the product of their asymptotic length and their instantaneous growth rate. And strangely enough, the inside growth rates are higher in the last 2 periods. This is counterintuitive, but it wouldn't be biology if we didn't find a counterintuitive result. Now I'm going to leave the counterintuitive results and step forward to those that make sense. Survival. It's a refuge. I would say if we don't find better survival in the refuge than out, we should immediately find other work. So we compared the age structures inside and outside the refuge. And the hypothesis here is that the survival ought to be higher inside the refuge than outside. So I'll show you the same sequence of periods. These are catch curves. The first thing to notice, of course, is not a whole lot of fish caught, and the slopes are the same. So we haven't seen the effect of the refuge in this first period. And strangely enough, not even in the second period, but by the 3rd period, the age structure is extending outside the refuge. This is symptomatically similar to the graph that Steve showed a couple of decades ago, only not quite as extreme, and then even more so by the 4th period. So now depicted as survival, consistently higher, but significantly higher in the last 2 periods inside the refuge. Good. I like it when things work out the way they're supposed to. And I would have dry labbed that first growth analysis, except I just couldn't bring myself to do it. All right, so the next thing I wanted to compare was maturity, inside and outside. And I remember Nigel Lester at a meeting once saying, if there's one thing that would be most symptomatic of density dependence, it would be age and maturity. Well, the maturity data were too sparse in the early period, so all we can compare is maturity in and out of the refuge in the most recent period, where we had enough samples. And our hypothesis here, in my thinking, would be that the fish would be older at maturity, inside than outside. Not sure about the length of maturity. And for starters, we'll show you that the length of maturity is not different inside and outside, but interestingly, age of maturity is a bit older inside, as you'd expect. So quickly to summarize this first phase, lake trout that were inside the refuge were more abundant. They grew faster to a smaller size, survived better, and matured at an older age than the ones outside. Mostly a clear picture that the refuge did something that one would expect. Now let's take a different look at this. So we can parameterize a model that has essentially 2 stocks, and all we need to do is move them back and forth using some reasonable guesses at how much they do that. So this is an age-structured simulation model built on the backs of some other graduate students who formulated these methods previously. The theory here is if you turn fishing mortality on and off, you could detect what the effect of the refuge would be on the future sustainability of the population. And that's easy to do inside a computer and doesn't take as long as waiting 30 years after implementing a policy change. So the model is a little complicated. Don't pay too much attention here except to note that we have a refuge population and we have a non-refuge population. The only difference between the two is that the refuge population has components for fishing mortality that we can tweak. You can display a wide range of fishing mortality rates. And then if you want to simulate getting rid of the refuge, essentially you just turn this on the refuge population. And we move them back and forth using rates of movement that we quantified in a prior study, one of those pieces of the puzzle I talked about. So to build a model, you have to start with something. And thankfully, the people that work in this zone day to day, like Mike Sider, they have parameterized the model quite nicely. They fit statistical catch-age models to the abundant data in the area. So we know the non-refuge abundance from about a 30-year model fitting in the zone, so we can take that as the starting abundance at age. And then we basically built the refuge population by using the weighted CPUEs in and out of the refuge, and then basically scaling the non-refuge to the refuge population. We had previously studied recruitment dynamics. Again, some of the people that did that are in this room. And so we have that piece of it worked out pretty well. And then the sea lamprey mortality, we basically take as a random fully selected rate and then scale it based on size selectivity from, again, the age and size specific estimates from that stock assessment model. And then last, we move the fish back and forth between the refuge and non-refuge waters. And so I'll show you a picture of that. This is based on that tagging data from the fall stuff, and it shows you how variable that rate of movement can be. So we have some uncertainty about in any particular year how many fish would move from one zone to another. You can see it's as high as 11% here, and it's as low as not observing any. That doesn't mean none of them moved. It means we just didn't catch any to observe. So we basically treated this then as a state variable that we would run different simulations over. The median is 2, the highest observed is 11, and so we took 2 times that as some estimate of how high it could be. So some of the results I will show you relate to this uncertainty about the movement rate. And you can also think about this in the context of refuge design. A refuge is properly designed if you can put it in time and space and deploy it, and it protects enough of the fish that you could do almost anything outside the refuge. That was the original conception of a marine protected area. The whole idea was we know that fishery managers are really lousy at protecting fisheries. The world record on, I mean, you could look at the tribunal on this, and we are really not very good at this. So if you recognize that, let's put something in place that protects the stocks from us. No matter what we do, no matter how bad we screw up, the stock will be protected. We ran the model 1,000 times, iterating over a 100-year window, and then varied the fully selected fishing mortality rates to basically probe how much fishing would be necessary to crush the population, regardless of the refuge. And I'm going to show you results for only one of the metrics we're recording. Basically, this is a surrogate for the adult fraction of the population. We have results for all of them. You basically use the first 50 years and ignore it, and then store the results over the last 150 years. We tallied the probability of collapse as the proportion of the simulations when the population declined by 90%, just an arbitrary measure of collapse. And then for extinction events, we just count those up, the number of simulations that go to, we're pretty sure that if you had no fish left, that means extinction. All right, so a little complex, but the picture here is showing this adult abundance from 1,000 iterations, and these are in hundreds of thousands of fish, versus this thing we're uncertain about, the movement rate. And I'm overlaying the shape of that relationship for an F of 0.4 with the refuge in place, an F of 0.6 with the refuge in place. And it's in this range of fishing mortalities where you get some real steep changes between having the refuge and not. Notice that at 0.6, this non-refuge scenario suggests that you have a lot fewer fish for this same fishing mortality rate than if you have the refuge. It's an important finding. The refuge actually produces more fish by having it, which is a little counterintuitive to the average person who wants to fish in the refuge. Their experience would be quite good for a little while, and then it would be really bad. Another result that's sort of important compares the fishing mortality rate that would cause the collapse. So that's on this axis. And then this is, again, the movement rate. You can see there's a dome-shaped relationship with the refuge where there's some sweet spot in here which is actually at a higher movement rate than we've observed, which is right around in here. And without the refuge, it's much worse. A much lower fishing mortality rate causes collapse without the refuge than with it. So that's important finding number 2. These are exactly what you would hope to find if a refuge was correctly designed. If it wasn't well designed, then you would see very little detectable difference between these two situations. Now I'm going to show you what actually the fishing mortality rate looked like for the 30-year stock assessment model estimates. And it's an important finding. This shows you the time series of fishing mortality rates. This is the fully selected rate added for commercial and recreational fishing. And then overlaying here is the F that would cause collapse without the refuge in place. And you can see that it's not so high that it's implausible. We've had observed fishing mortality rates that are flirting with this amount. So if you didn't have the refuge there, the suggestion is we would have fished harder than would have been necessary to crash the population. So now here's the probability of collapse versus the fishing mortality rate. Each line represents one of those different movement scenarios. And the key thing here is that when you have the refuge in place and you're just fiddling with the movement rate, the fishing mortality rate that causes collapse is quite a bit higher than when you either don't have the refuge or this mythical scenario where there's no movement. We know that no movement isn't real. It just represents a null basis for comparing the others. And now let's superimpose the observed fishing mortality rates from the stock assessment estimates. And this just shows you the hinge points of that frequency distribution of fishing mortality with the median in here. And the point is that these rates where we get rid of the refuge are very plausibly within the range of observed fishing mortality. A little higher than average, but there's not a lot of room for error here, whereas the refuge basically is quite protective. You would have to have extraordinarily high fishing mortality to cause extinction, or to cause collapse rather, with any plausible rates of movement. And now this is the years to extinction, the other metric we were keeping track of. And importantly enough, any scenarios that had the refuge in place, extinction never happened. The only 2 situations where we found extinction events was when we didn't allow fish to leave the refuge. So they couldn't do what the refuge was for, really. And then this represents getting rid of the refuge altogether. And now let's again substitute or superimpose the range of observed fishing mortality rates. And it's not likely that what's possible here is going to lead to extinction, but the fishing mortality rate that could cause extinction has been observed here. So if you didn't have the refuge in place, it's entirely possible this could just totally go bad. Little summary. The refuge ensured more lake trout were available for harvest over a moderate range of fishing mortality than if you didn't have it. And then that's an important finding. It's a long-term versus a short-term view of what a refuge is for. And then the probability of collapse, the refuge greatly reduced that risk at observed rates of fishing mortality. And finally, the refuge prevented extinction altogether, whereas anything other than the refuge allowed for it. So I'll just close with a little bit of review of the third project, where I'm now going to take this fairly parochial view of Lake Superior in this one area and say, what is the effect of the fact that there's a lot of fish elsewhere? And one of the old guys, Merle Keller, used to always say lake trout have tails. So that's why you need interjurisdictional management. They do cross boundaries. So we wanted to test the long-term sustainability of this zone, WI2, recognizing that fish are moving around. So this is the expanded view of the lake, and now each of these zones has had some stock assessments done on it. So we're now going to look at the focal point here where we change the fishing mortality in this zone and see what the effect of movement from all these other zones is. As you might suspect, the zones that are right next to WI2 probably both receive and donate more fish than those that are a long ways away. So you would expect the effect of movement from MI7 to be much less than, say, MI2. And to start off, I want to put in perspective the fishing mortality that was on the end of that time series from the stock assessment model in WI2 here is much higher than anywhere else. So notice in the Minnesota side of the lake, fairly low fully selected fishing mortality, and the next closest is in MI2, right next door, and then the rates over in the rest of Lake Superior on the Michigan side are really quite low. So I'm only pointing this out to give you a perspective on what WI2 is as a fishing zone compared to the rest, and perhaps to digest the punchline when I get to that. And that's depicted here. This shows you scenarios with movement and without movement. In other words, if you just sort of mythically shut off the movement of all the fish that could come into WI2 versus those that are leaving, the result here is fairly simply turned in sort of sink dynamics. This is a sink population. WI2 has great habitat, probably has great food supply, quite attractive to the lake trout. And so they swim over from Minnesota thinking it's great over here, only that they find themselves on ice in a fish tub. So it's not quite the haven they think. And in the setting of now thinking about WI2 with the refuge in place, you can see if you got rid of the refuge, all these things accumulate as huge risks for basically lake trout in this area. It is one of the better areas for habitat, for prey supplies, and that's probably reflected, and it had fairly high yield potential in the historic fisheries. Extraordinarily valuable zone. All right, so the summary of this, the median abundance, it tells you it's a sink population. They probably come here, or come to WI2 because it's great for them, at least until something bad happens. The immigration of fish from other zones prevents collapse in WI2, averts it, and there's no risk of extinction or collapse as long as those fish are moving around. So the simple punchline for us is I think getting rid of the refuge would pose some great risks. At fairly plausible fishing mortality rates, either you got to really restrain fishing or just simply keep the refuge. And remember, an MPA, or Marine Protected Area, was originally conceived of as a way around the hard stuff in fish management. If you just did one of the right design, you pretty much don't have to worry about the rest. Now, I'm not suggesting you don't worry about it, but I mean, the point is it appears as though this refuge was designed fairly well and is doing its job as you would hope from theory. So, thank you.